you can start. So welcome everybody to the second already international workshop on highlights in organizing and optimizing proof logging systems. Whoops. So we're going to have a series of tutorials today. And so I'm Jakob Nordström at the University of Copenhagen and Lund University. And I want to say right away that my slides are frozen. Let's see if we can get them to work. Yes, so this is what I'm going to talk about today, and what the other speakers are going to talk about is by now joint work with lots of people. I want to highlight the Bart Bogarts, Stefan Gocht, and Kieran McCreesh, who together with me designed the original VeriPB proof system that we're going to work on a lot. Benjamin Bugge, Vitse Kups, and above all Andy Örtel, who is working on the current version of the proof system. And then we'll talk a little bit today and more tomorrow about that you actually get formally verified proofs out of this. And this is work of Magnus Myrén and Joakim. So the background, I think, for why we're here is that since the turn of the millennium, there have been amazing progress in a number of different paradigms for combinatorial solving. So today, so-called Boolean satisfiability or SAT solvers, or constraint programming solvers, mixed integer linear programming solvers, are used to solve large-scale, real-world, NP-complete problems on a daily basis, very successfully. And there's only one small caveat. Sometimes the answers you get from these solvers are wrong, and you can get all kinds of errors. You can get solutions that are claimed to be feasible, but in fact are not. And you could say this is maybe not so serious, because then you can plug in your solution and check if it's actually satisfies your constraints. But a more challenging scenario is if the solver says that your problem is unsatisfiable, that it is infeasible. Or in some settings where you really need an optimal solution and the solver makes a claim of optimality, how can you know that this is true? And the answer is, in most settings, you cannot know. You can only hope. Well, this is an unsatisfactory state of affairs. So what do we do about this? Well, as computer scientists, we know how to deal with bugs. We do software testing. This is powerful, in particular modern techniques with fuzzing and delta debugging, but testing suffers from the problem in theory and also in practice that it can only detect that bugs are there. It can not make sure that we have removed all bugs. Another very appealing approach would be to specify formally what your solver should do, and then use formal methods to prove that the solver you have designed meets this specification. So it will be correct by construction. The problem is that what formal verification techniques can currently do just doesn't scale to the level of complexity of modern solvers. And this is despite, for instance, Matthias Fleury, who has done amazing work on SAT solvers, but it's just very, very hard to capture in a formally verified framework all the absolutely crazy things that modern solvers do in SAT solving, and it gets even harder for constraint programming or mixed integer programming. So I think it's fair to say that the only viable approach that we have today is proof logging. So what this means is that you make your algorithms, your solvers certifying, so that they output not only an answer to your problem, but also a proof that this answer is correct. So then the workflow is just as for any solver, you have an input and you get an answer, but a certifying solver also produces a proof, a machine-readable proof in a separate file, and then you have a simple standalone proof checker that can read the input, the proof, and the claimed answer, and can tell you whether you can trust the result or not. Okay. In order for this to work, there are two properties that you would like to have. On the one hand, we still want our solvers to be very efficient. We want them to run fast, so it should be easy to write proofs. And since solvers are doing a lot of powerful reasoning, this means that you need a powerful proof systems so that you can write down only short descriptions of what the solver is doing. But on the other hand, the whole point is that we don't want to trust the complicated solver reasoning. The whole point why we're doing this is that we believe that the solver is buggy, but now we've just reduced it. Now we have to trust the checker instead. And the reason we could trust the checker if it is if it is much simpler. Okay, so we want the proof system to be very, very simple, so that the checker is such a simple piece of code that we can just look at it and trust that it's doing the right thing. This is what we would like to do, and it's not hard to see that there's a conflict here. To make proof generation efficient, we want the proof system to be very powerful, but in order to trust the results, we would like a weak, simple proof system. So asking for both of these properties at the same time is maybe a little bit too good to be true. Except that the reason we're here for the Whoops workshop today is that we believe that there is a sweet spot in the middle between these two conflicting demands. So what we will tell you about is, firstly, we believe we should look at the SAT community, which has been very successful with a number of different proof logging systems that operate on disjunctive clauses. So we should basically try to steal all of their best ideas, but implement them for 0, 1 integer linear inequalities instead. And generate our proofs using the so-called cutting planes proof system, which with some suitably chosen additional rules, so-called strengthening rules that I will tell you about. This has been implemented in the so-called VeriPB proof system and proof checker, and we will tell you today how this works and then try to showcase a few of the things you can do. Before I get there, I just want to say that I believe proof logging, the starting motivation for us is to make sure that the results that solver compute are correct to get certified certificates of correctness, but proof logging is about much more than that. One thing that proof logging can give you that you don't get for formal verification is that if you have a formally verified piece of code but it runs on faulty hardware, then you still might not be able to detect that the result is incorrect. But if you're always generating a proof log, then if there was some kind of hardware issue, then the proof log will be incorrect, and then you will be able to reject the proof. One thing that we've seen in paper after paper also is that if you implement a solver with proof logging, then this can be a very powerful debugging technique, because maybe you have a large test set of instances and you get correct results for all of them, but then you switch on proof logging and you see that you're reaching these results by taking some shortcuts that most of the time doesn't matter because you're just avoiding some pathological corner case, but actually you cannot avoid this corner case because maybe someday there will be an extra solution lurking in there. Since the proof log that you generate with the certifying solver describes the solver reasoning, this also gives new tools to analyze what the solver is doing, to do performance analysis, and maybe detect ways of improving the solver further. By its very nature, the proof log that a certifying solver generates is enabling auditability. After you've run your solver, you can save the problem instance, the answer, and the proof log for posterity, and anyone can recheck it even if they no longer have access to your solver. And the proof log, since it not only typically certifies that you have the correct answer, but it will also be an explanation why this solution is optimal, for instance. This can also be, we believe, an important tool for explainability purposes, which, as you will know, is quite a buzzword these days. One more thing that I want to emphasize before we get into technical details is that when we're designing certifying solvers, we want to recycle all the amazing work in combinatorial optimization that has already been done. We're not looking to re-implement solvers from scratch. We want to take existing solvers with all their optimizations and just add proof logging to them. So you should think of the vision would be to just take an amazing, fast, efficient solver and just add judiciously chosen print statements so that when you string these print statements together, you'll get a valid proof. We want the proof logging overhead, the overhead for generating proof, to be small. what the SAT community achieves is something like a 10% overhead. Proof checking, we're not expecting it to be as efficient. The SAT competition currently allows roughly a factor 10 larger proof checking time than solving time. So this is what we're shooting for. For more efficient paradigms, as you will see later during the day, we're not quite there, but just to say that this is kind of our mental target, what we're shooting for. Then one particular design decision that we have made, it's not obvious you'd have to do this, but in our proof system, we want to keep the proof format very simple. So we will talk about exo reasoning, different constraint programming propagators. As you will hear later today, we'll talk about symmetry breaking, and there will be groups and orbits and stuff, but the proof system doesn't know about any of this. So the proof system basically only, as we'll see shortly, only knows about Boolean variables and linear inequalities over such linear combinations of such variables. And still we'll be able to reason about all of these different notions by using the rules of the proof system. This means that if our input problem is talking about something other than linear inequalities over 0, 1 integer linear variables, then we need a translation step. And here is where we would like to make a combination with formal verification techniques to make sure that we translate the original problem correctly to this simpler formalism. And this also can be done. We won't really focus on this during this tutorial today, except we'll see a little bit of it maybe, and again, I think we'll see more about this tomorrow. So what we're doing now is in this first tutorial, I'll talk about the basics and also start from what the SAT community has been doing with proof logging for SAT solving. And then before lunch, we'll hear about subgraph solving and constraint programming, where we will already go way beyond the base format of just Boolean variables. And after lunch, we'll hear about pseudo-Boolean optimization, about pre-processing, and finally about symmetry breaking. So that's the plan. And you should feel free to ask questions at any point, because this is all about obviously trying to explain. So it's not about me trying to get through my slides as quickly as possible, but hopefully about conveying information to you. So when anything is unclear, please do ask. So let's start from the basics. We'll talk about SAT. We'll need to talk about the DPLL and CDCL algorithms used for SAT solving, where unit propagation is an important concept. Turns out to be important also for our proof system. And we'll talk a little bit about what the resolution proof system is. So just to make sure we're all on the same page, we'll start now for a few minutes at least. We'll talk about formalizing conjunctive normal form, like the one at the bottom of this slide. These are conjunctions of clauses where every clause is a disjunction of literals, so variables or negated variables, where overline denotes negation. And we want to assign the variables true or false, so that all these clauses are satisfied, that they have at least one satisfied literal. Okay, and throughout this talk, true will be 1 and false will be 0. So if this is going too slowly, you should look at this CNF formula, and the question we're asking ourselves, is there a satisfying assignment to this formula? Or is it the case that however I set these variables, I will violate some clause? This is what the SAT problem is. Okay. So when you're solving a CNF formula, what would a proof be? Well, if there's a satisfying instance, like I didn't hear anyone saying this, but if there is a satisfying assignment, you should be able to just tell me that, set PQ, P true, set U also true, maybe Q false and R true or something. And if you just give me this assignment, I can just plug it in and check. Right? So in that sense, proofs for satisfiable instances are not complicated. But in fact, if you try to plug in all of these, you maybe try out a few different assignments, you will figure out that none work for these formulas. So maybe this formula is unsatisfiable. What would a proof be of unsatisfiability that we could check? I can tell you that it's unsatisfiable, but that's mostly a proof by intimidation. How can I give you a more convincing argument? And what our proof will be, I will tell you a sequence of new clauses where you will be able to verify for every clause that, well, if the original formula is satisfiable, then clearly I can also satisfy this new clause. And I'll give you these clauses one by one until I give you an empty clause that contains no literals at all, which means that it's a contradiction, and we write it bottom. And since every clause followed from previous clauses and I've now derived contradiction, we have to conclude that the original formula is unsatisfied. This is what a proof means. But what do we mean for something to be obvious? Well, here is where unit propagation comes in. So we say that a clause unit propagates a literal to true under some partial assignment row if the assignment row falsifies all literals in the clause except this one literal, which then has to propagate in order for the clause not to be violated. So here's our example formula again. Let's suppose I set P and Q both to false. Let us unit propagate just to see if we're on the same page to understand this. So P is now false, Q is now false. Then from the first clause you see, well, there's only one non-falsified literal left in the first clause, namely not U, so U has to propagate to false. Similar in the second clause, there's only R left that is non-falsified, so R has to propagate to true. But then not R in this clause turns false, which means that W propagates to true. And note that I write down here the reasons for why I have these propagations. We'll refer to these later as reason clauses. And now if you look at this, you see there are no further propagations. All clauses are either satisfied or they have at least two unassigned literals, so no further propagation. And now one basic property of our proof system will be that if we tell the proof checker about something and it follows by unit propagation, then this is such a simple procedure that our proof checker is expected to be able to do this. Okay, so now let's see, what did people do for SAT solving back in the 60s? Well, they just basically did a backtracking search. So let's do this for this formula, and whenever we have to backtrack, let's write down that we've learned that one of the guesses, one of the decisions we made so far is false. So we start by guessing that maybe X is false. Nothing much happens. I guess that Y is also false. And now you see that if X and Y are false, then U has to propagate to true. Well, if U propagates to true, then P has to propagate to true. But then this clause is violated. And so we've learned now we have contradiction. So it can't be that X and Y are both false. Let's write this down. Okay. So then I try to swap U to true instead. But then this clause propagates Z, which violates this clause. So now I learned that either X has to be true or Y has to be false, which means that I've tried both values for Y when X is false, so X has to be true. And I'm writing down these backtracking clauses as a trace of my proof search. And now if I try to set X to true instead, then you see that this clause over here will propagate Z to true, but then this clause is again unhappy. So setting X to true also didn't work. So now I tried both values for X and I can conclude that the formula is unsatisfied. And this sequence of backtracking clauses is like a trace of my search. And the point I want to make now is that we want this to be a proof. And it, as you could sort of already see when I ran the proof on the previous page, it is kind of a proof, because what I can do is I can claim these backtracking clauses. I can show that they're implied by reverse unit propagation. So what is reverse unit propagation? I say that a clause follows by reverse unit propagation from another set of clauses F for a formula F. If I violate the whole clause, I set all literals in the clause to false and then just apply unit propagation. And if when I do this, I hit contradiction, this shows that, well, C cannot be false except if F is false, which means that if I turn this around by contraposition, if F is satisfied, then C has to be satisfied, which means that F implies C. Okay. And now it's a simple fact that if you take this DPLL tree-like search that I showed you, and you just write down the backtracking clauses, then this sequence of clauses will be a RUP proof. And you kind of saw it because that was what I was doing when I was running the tree-like search. But that's back in the 60s. Nowadays, SAT solvers do conflict-driven clause learning. So let's see how that works. So here is our favorite formula again. So here's like a crash course of SAT solving. What the solvers will do again, just as for DPLL, they pick variables to branch on. Let's suppose we do variables in alphabetic order. So we pick P first, and we decide, this is what this D means, to set it to false. Okay? And then whenever the solver has made a decision, it will try to propagate. So it looks if there are any forced assignments by unit propagation. And here in this case, we see that, well, if P is false, then the first clause will propagate that U is also false. And I will refer to P or not U as being the reason clause for this propagation. Now nothing more propagates. So the solver sets the next variable, say Q, to false. Then we can again propagate Q or R, propagates as R has to be true, which propagates then the third clause propagates then in that case W has to be true. Then there are no further propagations again. So then I make a decision. I set X to false. If X now U is false and X is false, so U or X or Y propagates that Y has to be true. Now X or not Y or Z propagates that Z has to be true. But now this clause is violated and we have a conflict, just as we had before in DPLL. But now a modern solver will do something that's called conflict analysis. Well, just one more thing that might be a little bit helpful is to say that in a SAT solving terminology, the decisions I make together with all propagations that follow is often referred to as a decision level. So here we had 3 decisions and we reached a conflict at decision level 3. What a DPLL solver would do, it will just say that, well, clearly setting X false was bad. I want to flip this decision. We want to instead do something slightly smarter. We want to derive a reason in the form of a new clause why we made this, why this partial assignment didn't work. And the hope is we will then add this new clause to the formula and hope that it will cut away the search space as we continue. So looking just at these last 2 clauses, we see that the last one wanted Z to be false, but this reason clause wanted Z to be true. So we can just take their union and remove Z and see that, well, any assignment that should satisfy these 2 clauses also has to satisfy X or not Y, which is what I've written here. This is a new clause that we don't have in our formula, but that clearly follows from the formula. Now I can repeat this again. I can look at this new clause, which wants Y to be false. This reason clause here wanted Y to be true. Again, I can take their union and just remove Y. And I learned that U or X has to be true. In any assignment satisfying this formula, I have to set either U or X true. And now we don't really have time to go over the details. But now if you look at this clause, it only has one variable from the last decision level. It's a so-called first UIP or asserting clause. And there the SAT solver will stop and say, let me learn this clause. Let me add it to my database of clauses. And back jump. And basically, when we back jump, we remove decisions and propagations from the trail, as many as we can, but while this constraint is still propagating. So we remove the decision on X, we remove the decision on Q, we keep the decision on P and the propagation on U. And note now that with this partial assignment, P and U being false, this clause will immediately propagate. So in the end, we just flip the value of X, but the difference now from DPLL would have just made this as a decision, but now we know there's a reason for it and we will never go back. So now the solver just continues again. It propagates, so not X or Z, propagates Z to true. Then this clause is violated. We do a conflict analysis. This time it's really easy. We just derive that not X has to be true. So X has to be false in any satisfying assignment. So then we back jump all the way to top level. And this so-called unit clause propagates. and then u and x, this learn clause propagates that u has to be true. Then this clause propagates again, but now it says that p has to be true, and this makes this clause unhappy because it wants p to be false. And now the solver will terminate and say this formula is unsatisfiable. We can, in our head, run conflict analysis again. If we did, we would derive not u, then x, and then we would say, well, if x has to be both true and false, that's contradiction. Okay, so that's a few minutes on modern chat solver. And now we want a proof for this. So what would a proof that would certify the correctness of this reasoning be? Well, this is nothing other than a proof in the resolution proof system, actually, where we start with the clauses of the formula we want to prove unsatisfiable, and then we can derive new clauses by the so-called resolution rule that says that if we have derived the clause c or x and another clause d or not x, then we can derive c or d. And a resolution proof of unsatisfiability is applying this rule over and over again until you derive contradiction in the form of an empty clause. And note that we even use bottom contradiction to denote it. And a modern CDCL, conflict-driven closed-learning SAT solver, actually generates a resolution, explicitly or implicitly. This is ignoring preprocessing. We'll get there later during the day. But sort of most of the basic CDCL search algorithm generates a resolution. And just to see this by example, here is our execution again. I can just take the conflict analyses, which are actually small resolution derivations. I just string them together, and now I get a resolution. And this is something that works not just for this small example, but this is like a general thing, which obviously would need a proof, but we don't have the time for this. So I do proof by picture. However, if I wanted, this is still a fairly large proof. So if I want to minimize proof size, it turns out that I could actually be slightly smarter. I could get a smaller proof at the cost of making life slightly harder for the proof checker. Because all the clauses a CDCL solver learns, they're guaranteed to be verifiable by reverse unit propagation. So here is just a list in order of the clauses I derived, or the solver derived, and I claim that they're all wrong. So let's see this. First, I start by setting u and x to false. If u and x to false, u and x are both false, then y propagates to true. That propagates z to true, which violates this clause. So I asserted u or x to false, and I violated the formula. So this clause clearly follows from the formula. Next, I assert not x to false. That means setting x to true. Well, setting x to true propagates z to true, which violates this clause. So I know now that this clause also follows from the formula. And now I'm done. Now I'm just saying, well, now I'm claiming contradiction by reverse unit propagation. Well, what does it mean to do reverse unit propagation on negation? It means doing nothing, because claiming the opposite of contradiction is claiming truth. So I'm basically claiming bottom by reverse unit propagation is say, just unit propagate on the formula now, and you will get contradiction. To see that this happens, first we propagate on, clearly this clause says that x has to be false, but then this clause says that u has to be true, then this clause says that p has to be true, and now this clause is violated. So I had to spend more time verifying now, but note that my proof comparing to what I had before, okay, that's animation takes some time, but here I had like 8, I guess something like 13 clauses maybe, and now I got the proof side down to just 3. Okay. And this is actually all the same, because reverse unit propagation proofs, if I just list the sequence of reverse unit propagation clauses, that is actually just a shorthand for a resolution derivation. If you want to know more about this, there's this survey I wrote together with Sam Bass, which is in the Handbook of Satisfiability. So basically, the basic conflict-driven closed-learning search, all you need is the resolution proof system, or even just the concept of reverse unit propagation to write proofs. But there are some forms of reasoning for which this is not enough, namely preprocessing. So for this, we could introduce an extension rule. I can say that if A is a fresh variable, then it should be okay to just introduce these three clauses: A or not X or not Y, not A or X, not A or Y. This is basically, if you look at it, this is defining A to take the same truth value as the conjunction of X and Y. And again, we don't have time to go into too much details, but this, if I take the resolution proof system I told you about before, or RAP, and I take this extension rule, this is essentially what modern proof logging systems in SAT contain. Proof systems like the DRAP proof system. Okay. So far, now we've covered basically what SAT proof logging is. Yeah. And the question is, yes?
Could you go back to, well, you said root, you only have one clause, and resolution you have many, right? But you could forget about the intermediate ones and just give the ones that resolve to get the root. So root plus the clauses that allow you to get a contradiction basically give you a resolution, right?
Yes. Yes, that's it. I mean, sort of what I'm saying is, when I'm running these reverse unit propagation checks, if I just turn them around, then I would actually get a resolution proof. If you, what is true in general, which again requires a proof, but if you look at my RAP checks, were essentially just running these resolution derivations in reverse. So they're really kind of the same thing.
But my question, would it be very costly to add with RAP the ID of the clauses that actually prove, so that you don't have to do watch literals and stuff like that to do the RAP?
Then you would do not DRAT but LRAT, indeed, as maybe Florian Pollitt will tell us tomorrow, maybe. Yes, if you want your, this is again a trade-off between, you know, how much work do I want to do to generate the proof and how easy should it be to check. But you could argue, well, if I did this conflict analysis, I kind of know these ideas. So why don't I just print them out? The proofs would be slightly longer, but maybe not too bad. And you could think that this would probably speed up proof checking, which is what you're saying, right? And the answer is, I think the data is that yes, significantly. Like, this is a really good idea to speed up proof checking. Yes. Okay, so, but then why aren't we done? You know, we're only halfway through the first lecture, and we're going to keep going a whole day. Well, the problem is that this proof logging with just clausal constraints and resolution and the extended resolution rule turns out that it's not quite sufficient to deal with strong forms of reasoning, even for SAT solving. And also, if you go to stronger types of algorithms, we'll hear about subgraph solving and constraint solving next. Clauses don't really reflect the kind of knowledge that these solvers derive. And basically, you know, a one-sentence version of what we're going to do during the rest of the day, we're just going to take this and we're just going to say, what would all of this mean if we do it with 0-1 integer linear inequalities instead? And this is all that you need. Okay. Then it turns out that this takes you pretty much all combinatorial solving and optimization paradigms we've studied so far. It turns out that the SAT ideas, but translated to 0-1 integer linear inequalities, just works. So in particular, for things like cardinality reasoning, Gaussian elimination, and symmetry breaking that are advanced SAT techniques that DRAT cannot quite support, you can support it if you change to 0-1 integer linear inequalities instead. You can also then get proofs when you use SAT solvers for optimization, so-called MaxSAT. You can do proofs for sophisticated graph algorithms, although the proof system doesn't even know what a graph is. And you can also do proofs for constraint programming, although you have no idea what an integer variable is, or like what a string is, or whatever. And this is something that Kieran McCreesh and Matthew McGillary will soon tell us about. So let me finally then get to what the proof system is that we want to use. So we're going to operate not with clauses, but with 0-1 integer linear inequalities. In particular, integer linear combinations of literals, so again, variables or negated variables, greater than some other integer. So the coefficient and the constant term, the degree of falsity, are all integers. Sometimes it's convenient to insist on all these integers being positive, and this we can always achieve without loss of generality because we can flip signs of literals. This is called normalized form. I will not emphasize this. Most of what we do doesn't care about normalized form, except that sometimes it's helpful. And just to make sure we're on the same page, note that this is a strict generalization of clauses. A clause is just saying that the sum of the literals is at least 1, but you can compactly express more interesting things like a cardinality constraint, at least 2 out of these 4 variables are true, or something more general that x plus 2 not y plus 3x plus 4 not x4 plus 5x5 greater equals 7, something like this. Yeah. So this is our the constraints in our language. This is what they look like. Our proof system then takes the input, it's encoded to 0, 1 integer linear inequalities, and then we know that all literals, variables and negated variables, are non-negative. We know that if we have 2 linear inequalities, we can add them, we can multiply them by a positive number, we can divide by any positive integer and round up. This is also known as a Quatal-Bomori cut. It's exactly the same. So if this is a true inequality, then I can just divide by a positive integer and round up. And this is basically all that we need, but just for completeness, there's also a so-called saturation rule, which if you're from an operations research background, you will call this coefficient tightening, which says that if I have normalized form, so if this is a positive linear combination, then I can trim these coefficients down so that nothing needs to be larger than the right-hand side, than the degree of form. And let us not stare too much at these rules. Let's just do a toy example. So suppose that this is an input constraint, then I can multiply it by 2 and add it up with this other input constraint, say, and if I add them up, then I get 3w plus 6x plus 6y plus 2z greater or equal 9. So I can do in my proof system. I can also say that I know that z is less than 1, or that not z is greater or equal 0. I can multiply this by 2 as well and add up. And now note that I have a cancellation here. So z and not z cancel to leave a 1. 2 times this leave a 2, which I shift over to the right-hand side. And now I can divide. And note that I get a fractional value here. But since we know that everything is integral, I can just round up. So this is what like the derivations in our proof system will look like. And now when you write them in a proof file, the variable z is just z, the negated literal not z, negation is a tilde. Every constraint gets a number. So let's say that this is constraint number 1 and this is constraint number 2. Then this proof tree, when we write it in the proof file, will just look like this. Here's a line by reverse Polish notation. Take constraint number 1, multiply it by 2. Take constraint number 2, add the things you have so far up, add them up, then take 2 times z greater equal, not z greater equal 0, add this up, and finally divide by 3. So this is just a line in reverse notation. I'm doing this slightly fast, but hopefully it's somewhat convincing that any derivation like this, I can represent with an ASCII string like this. Does that make sense? So this is like what lines in our machine-generated proof file will look like. And just to see that this is also sufficient to do proof logging for SAT, if I take these 2 clauses and resolve them, then as linear inequalities, not x or not z, that's just not y plus not z. The clause not y or not z is just not y plus not z greater or equal 1. X or not y or z is just x plus not y plus z greater equal 1. I can add them up, and then I can divide by 2, and this is just the resolution step. And this is like a complete generic thing. I just add and divide by 2. That is essentially resolution. And again, how would I write this? Well, in my original CNF formula, this was clauses number 5 and number 7. So I would again write a proof. Here comes a line in reverse Polish notation. Take constraint number 7 and number 5, add them up, and divide by 2. Yes?
You could also just saturate.
Absolutely. As Daniel is pointing out, I'm kind of ignoring saturation here, but Daniel is absolutely correct to point out that I could also here equally well have used this saturation rule. So that's a good point. Let's see why. Well, because here, note that I divide by 2, but I could just have said, let me trim this coefficient. This is larger than the right-hand side. Let me trim this down to 1.
So that means that you have two different ways to reach this. So is it a problem or?
No, you can write it in fact, if you want to be efficient, this is maybe a question for Andy and Benjamin and Vitze. I would guess that doing this proof with saturation should be slightly faster, but
yes.
But it's like, I mean, yeah, not a big deal. Maybe. Just that I don't want somehow I'm keeping the rule set as simple as possible. Just to see again, what would suppose I want to do a proof for this conflict analysis in our new proof format. So here was the proof again. So here are every clause. When I just read the formula in memory, every constraint, every clause gets a number. So the first conflict analysis just says take clauses 7 and 5 and resolve them, and then resolve this with clause number 4, and you're done. And then this will get, when I do this, this new clause will get the next available number. So this automatically becomes constraint number 10, and it will look like this. Note that the proof line doesn't say what I've derived, but this we can just compute, and we know that it's this clause. Okay, and then the next conflict analysis says take clauses 8 and 6 and resolve them. And this means that this will now be constraint number 11. And then this final conflict analysis is this longer string. Okay. So a CDCL stat solver execution conflict analysis for this would basically be a sequence of line squares. Or you can also generate, you can generalize reverse unit propagation to this setting. And I won't go into too much details exactly how you do this, but just as by example, suppose I have this constraint again, and suppose I tell you that x5 is false, and you look at it, then you realize that, well, if I don't set x4 to false now, then the constraint will definitely be violated, because 1 plus 2 plus 3 is 6, which is less than 7. So if x5 is false, then this constraint will actually unit propagate, not x4. Okay, and again, there is a formal easy criterion for this, but just in the interest of time, I won't go over it. So this is something that, if you're from a constraint programming background, my constraint programming friends tell me that they would call this maybe reverse integer bounds consistency. But it's sort of, it's interesting when you work with pseudo-Boolean constraints, and this is one reason also to be careful if you come from a SAT background, because in contrast to clauses, constraints can unit propagate now several variables, not just one, and it can also propagate at different levels. Like I said, one variable, and then I get one propagation. Later, I said a few other variables, and now the same constraint would propagate again, but some other variables. And that it would not be hard, incidentally, to cook up such an example here. If I said x5 to false, then x4 would propagate to true, and then I have no further propagation. But now if I set x3 to false, then the constraint would propagate again, and then it would propagate both x1 to true and x2 to false. So I can also define then reverse unit propagation. That just means add the negation of the constraint and propagate. And our shorter RUT proof would then look like this in a pseudo-Boolean proof law. This is basically just asserting first that u or x has to be true, then I'm asserting that x has to be false, and then I assert that 0 has to be greater or equal 1. That is, I'm asserting contradiction. We can also do extension variables, which is sometimes called reification. So I can introduce a new Boolean variable that is true only if this, say, 0-1 interlinear inequality, if this pseudo-Boolean constraint is true. If you think about it, this is these two constraints. The first one is easier to say that clearly this implies that if A is false, sorry, if A is true, then this inequality must hold. This one is a little bit harder to see, but basically what it says here that if A is false, then there's no way this constraint is true, because the negations of the literals will sum up to at least 5, and the total sum is 7. So that means that this will be at most 2. That is the constraint is violated. And for this, we again need some special rules that we'll talk about in a minute. And this is one of the so-called strengthening rules in the proof system. So now in this proof system, what are our proofs? Again, for satisfiability, for satisfiable instances, you just give an assignment. For unsatisfiability, we'll now have a sequence, not of clauses, but a sequence of pseudo-Boolean inequalities, which we write in the so-called OPV format, which you've already seen on previous slides, where again, each constraint follows obviously from what is known so far, either by reverse unit propagation or by an explicit cutting planes derivation, or as I did on the previous slide, I could also allow myself to just introduce new variables with reification. And then in a proof by contradiction, the final constraint is 0 greater equal 1. And I'm cheating a little bit on the strengthening rule. We'll see more details about that in a little bit. But this is basically what pseudo-Boolean proofs are. One thing that I'm omitting is that in practice, it's important to, if you keep going and generate more and more constraints, then it will become costly to keep track of these constraints after a while. So it's important to delete constraints. For unsatisfiability proofs, deletion doesn't pose too much of a problem. If you're doing a proof for an optimization problem, then you have to be really careful. I'll mostly ignore this for now. We'll mostly ignore this during the whole day. I think we'll hear a little bit about it when Andy Oertel gives his talk about preprocessing. But basically, it's not a problem, but it's a little bit more complicated than you would like for optimization problems. You can, so talking about optimization problems and enumeration problems, if you have an enumeration problem, then there's a rule that basically says, I found a solution, please exclude it. So then the proof checker will check that this is indeed a solution, and then it will introduce a new clause or constraint saying, please don't ever show me this solution again. And if you do this and finally derive contradiction, then the semantics of this is, well, the sol x rules have told me about all proofs, and except for this, there are no other. The sol x rules have told me about all solutions, except for that, there are no other solutions. For an optimization problem, we can deal with a linear objective, which is a linear integer form over literals that we minimize, subject to constraints in the formula. If you want a maximization problem, just negate the objective. And now there is another rule for finding solutions, where you check that alpha is a solution, and if it is, then you get a so-called objective improving constraint that says, from now on, give me strictly better solutions. And then a proof of optimality, if you derive contradiction after having a constraint like this means that, well, the last solution I told you about was best possible. They claim that there is something strictly better than this is a contradiction. But you don't, one thing that is important to understand is that you don't necessarily need to have exact proof of optimality. You can also write a proof that finds a solution, and then prove some kind of lower bound that is maybe not fine. So you can write a proof that establishes an upper bound and a lower bound, and then you get an interval, so that you still know at least how far off you are. So if your problem is now a CNF problem, or if it's a 0-1 integer linear program, then you're in luck. Basically, your problem is already in the right format. To do proof logging, you just add print statements to your amazing solver, except that, as we'll see later, and maybe Daniel will tell us about this tomorrow, well, it's not maybe as easy as it sounds. We'll get back to that. Otherwise, if you don't have a 0-1 integer linear program, you have to translate it to 0-1 ILP somehow. But this is a very expressive formalism, and often you can do this in a clean way. For instance, for example, for graph problems, if you want to solve max clique, there's like an obvious 0-1 ILP that in some sense is max clique. The important thing to understand here that if you do this, you will generate your proof for the 0-1 integer linear program, but your solver will not be a 0-1 ILP solver. Your solver will still be working with the original problem and do its original reasoning. It's just that you print the proof print statements as 0-1 integer linear inequalities. Okay, so why would we do this with 0-1 integer linear inequalities rather than clauses? Well, it just seems that 0-1 interlinear inequalities are much more expressive. And the fact that this cutting planes proof system that I told you about seems powerful enough to capture a lot of what we do in different combinatorial optimization algorithms. Also, there are some nice features. For instance, this reification that you saw with big M constraints. Here's another example, just to flash it again. Suppose I want to say that this constraint we saw before, suppose I want to define a variable R that is equivalent to this constraint, then I can write it down within the language as these two constraints. So I don't have to go outside of my language. These kind of reification constraints are already in my language, and I can nest them in several levels. And the proof system allows me to sort of go in between different levels of reification nesting in a very efficient way. And I think this is also one difference if you compare to DRAM proof logging, where this would be a major pain. If, however, your input is not a 0-1 interlinear program, this means that the setup is now slightly different, because the solver kind of says, well, here's the 0-1 interlinear program that is translating my input, and for this I have the following. And now you can do one of two things. Either this translation is so simple that you somehow trust that you got this right, but if you really want to prove, then what you will do is you'll have a formally verified checker that checks that these two line up. And for this formally verified checker, typically you can run our checker as a preprocessor, which simplifies and elaborates the proofs so that the formally verified checker gets the input, the encoded input, the elaborated proof, and then if you believe that Isabel or Lean or whatever is correct, then you should believe the verdict of the formally verified checker. We won't emphasize this point today, but this is sort of what we're aiming for when we do proof logging, to have this kind of tool chain. Okay. Okay, we started very late, so I think maybe I'll steal a few more minutes, and then we'll maybe start late the next section also, a few minutes. So let me just tell you briefly about strengthening rules. So clearly, one thing that we can do with the rules derived so far is we can derive implied constraints. But again, if I want to derive that a fresh variable A is equivalent to this constraint, clearly I can do it with an implicational rule. There's nothing that implies that A should take the same Boolean value as this inequality. So I need another rule, like all the cutting planes rules that you saw, they just derive things that are implied, but these constraints are not implied. So we need something that can do, but these constraints are not implied, but they're clearly fine because A is fresh, it doesn't appear anywhere. And certainly it's fine to define A in this way. I mean, I can do it. So we need proof rules that would allow me to do this. And in general, that would allow me to do without loss of generality reason. So this you can do with a rule that's called redundant space strengthening, where we say that a clause is redundant with respect to another set of constraints. This is not necessarily a clause, by the way. This could be a pseudo-Boolean inequality, sorry. Is redundant with another set of constraints F if, when I add this constraint to F, it doesn't change the satisfiability status. So F and F union C are equisatisfiable. Now the choice of terminology redundant is a little bit unfortunate because most logicians would say that this whole definition kind of means that C is not redundant, but we inherited this from the SAT community and we have not tried to change it. So if you accept that this is the meaning of redundant, then you can see that actually C is redundant with respect to a set of constraints F, if and only if the following holds. There is a substitution omega. The substitution is something that maps variables to truth values or literals, and we'll refer to this substitution as a witness, for which the following implication holds, namely that F union, the negation of the constraint, implies F union, the actual constraints, if I plug in the substitution omega first. So this notation means take omega and plug it into all of these constraints. So this is a little bit, let me see if we can unpack what this means. So I claim that the interesting proof direction is that basically this says that if this condition holds, then I can add the constraint C to F and it won't turn unsatisfiable. Okay? So what is it that could happen? Well, it could be that we had a solution alpha that satisfies F, but that doesn't satisfy C. Well, if so, alpha satisfies F and it satisfies not C. And then this implication tells us that, well, if alpha satisfies F and not C, then alpha will satisfy this right-hand side. It will satisfy F union C under omega. But now we just have to unpack what this means. This means first apply omega, then apply alpha. So it means nothing other than that the composition of alpha and omega satisfies F unions. So the semantics of this rule, like operational semantics, is that this witness omega is a way of saying, well, if I have an assignment that worked before but violates this new constraint, omega tells me how to patch it to get a new satisfying assignment. Okay. And it's important to, when I do this in a proof log, everything has to be explicit. I have to write down omega. And for all of these constraints on the right-hand side, I need to be able to verify the implications. For instance, maybe they follow by reverse unit propagation, or if they don't, I will have to write down explicit subproofs in the cutting planes proof system. Note that these are semantic implications, so I can write down cutting planes proofs for them. I think in the interest of time, I'll do this just very quickly. But suppose again, this example, suppose I want to define A to have the same truth value as 3x plus 2y plus z plus w greater or equal 3. Then I can derive these two clauses using this redundant space strengthening rule. And what should my witness be? Well, intuitively, the witness should reflect, why do we know that this is true? Well, because A could just take the value, the Boolean value of this constraint. So the reason that it's okay to add this constraint is that, well, I could always set A to false, and then this constraint is values. And this is what would happen in the proof log. I would just choose the witness A to be false, and then it's kind of clear that I need to prove this, but this new constraint is satisfied, it's vacuous, and omega didn't touch anything else of F, so clearly this implication holds. Then when you want to add the second constraint, this is okay to add because you can always set A to false. This gets a bit more complicated. In the interest of time, I think I'll skip over it. The slides will be online later. But basically, again, you will just see that if you set A to true, then this constraint is vacuously satisfied, and this constraint obviously follows from this. In fact, this constraint here obviously follows from this constraint. And this is easy enough that the proof checker can just see. Again, I'm skipping some of the details, but this is a general thing. These type of verification proofs are very easy to check. They follow by obvious implication. If I have an optimization problem, then I have to be a bit more careful. I need to make sure that when alpha remaps my solution, it's not allowed to make the objective larger. So F under omega, little f for F, the objective should be at most F. So this is another proof obligation that I have for optimization problems. And now, interestingly, you can look at this and you can say, well, suppose that I can have a stronger promise from omega. Suppose I can prove that omega actually will make my objective strictly smaller. It will strictly improve my objective. Then I can strengthen this rule and say, well, in this case, you only have to prove F, but you don't need to prove C. Okay? And this is something that we call dominant space strengthening. It's slightly incomparable. I have to prove something stronger over here, but I have to prove something weaker over here. And as Marcus will tell us after lunch, this turns out to be super useful. The only question is, why is it even so? Okay, so let me try to run a very quick argument for this. Suppose that we have an alpha solution that satisfies F, but falsifies C. That means that it satisfies not C. Well, then alpha composed with omega satisfies F, and alpha composed with omega also gives me a strictly smaller objective. And now we have two possibilities. If alpha composed with omega satisfies C, we're happy. Otherwise, we're in the same position as before, and we just compose alpha composed with omega, and we again get a new assignment that satisfies F and gives us a strictly better objective. And now if this alpha composed with omega twice satisfies the new constraint C, then we're done. Otherwise, we're in the same position again, and we just compose alpha with omega 3 times and get a strictly better objective again. But the objective is an integer which has a lower bound, so this can't go on forever. So by induction, this process will have to terminate with an alpha prime that satisfies both F and C. But note that I don't have to run this whole inductive argument. I just have to prove this on one line, and then this is just the soundness argument, but the proof checker doesn't have to do it. And this turns out to be very useful. It can even be made stronger if I've derived a couple of previous constraints from F with semantic rules of using dominance, then I can derive the new one if F union all the previous ones union negation of my new constraint implies F under omega plus strict improvement of the objective. But I don't have to worry about these guys. This turns out to be very, very powerful. I can use them as premises when I prove things, but I don't have them as proof obligations. And you can prove this either by a nested inductive proof, or you just, in your proof, you say, let's pick a solution alpha that is satisfying F and already minimizing F. And then if this holds, you can see that such an alpha has to satisfy everything. I'm doing this very, very quickly. I mean, clearly this requires a proof. And you can actually you can generalize this even further. And I refer to this paper. By the way, all references are at the end of the slides. Slides will be online. So I'm obviously skipping some proofs here, but the point is that this is a sound derivation rule, and it turns out to be really useful. And just to flash what it would look like in the proof file, you would write by redundance, and then you would list your constraint. Here comes the witness, and then you would potentially have a list of subproofs, except that for what we saw before, you wouldn't have any subproofs because all of these are so obvious that you would just write them down and write down the witness, and then leave the rest to the proof checker, and the proof checker would say, yeah, I don't need any subproofs, that's fine, I'm figuring this out on my own. But the important thing is to say that the witness has to be explicitly stated in the proof log, and all these proof goals that you had here, they have to be either obvious, or followed by reverse unit propagation, or followed by some other very, very simple syntactic checks that the proof checker can. The surprising thing, and the reason why we are here today, is that what I've told you about now is sufficient to do pretty much all advanced techniques in Boolean satisfiability solving, which wasn't possible before. You can do proofs for SAT-based optimization. For pseudo-Boolean optimization, and we'll hear about pseudo-Boolean optimization later today. You can do subgraph solving. This is something that we'll hear about next. You can do, if you have a dynamic programming algorithm, if you're reasoning with decision diagrams, there are nice proofs in this formalism. You can do 0-1 integer linear programming. So far, we only did it for pre-solving, but in principle, you should be able to do it for the full algorithm. There's a sequence of papers of constraint programming that we'll hear more about. Tomorrow, we will even hear that you can go beyond NP and do P-space complete problems like planning with proofs in this formalism. And I think we don't fully understand why this works, but it does. So it seems to be like a really powerful, well, you can say either this is a really, really powerful proof system, or maybe we're not as smart as we think when we design combinatorial optimization. Either way, it's like this turns out this is all these different solvers that on the face of it reason in very, very different ways. You can capture it in one unified proof system. If you want to know more about this, we have a bunch of tutorials. The most recent ones are from Whoops last year. We'll put the ones online from this year as soon as we can, if the recording works. And the reason you should maybe wait for Whoops 95 is that the proof system has been slightly cleaned up and updated. So everything mathematically is still correct in these previous tutorials, but the syntax has changed slightly. The new syntax you also find if you wanted like the technical documentation the full truth, you should go to the SAT competition webpage. This is the best technical documentation we have so far. If you want to see the math, like how do you do the proofs for all of these different reasoning techniques, you can look at the papers. Many of them contain worked out examples. Again, there are full references at the end of the slide. And you can also go to the VeriPB repo, where there are lots of explicit example files that are maybe being transferred to the new syntax also as we speak. There are still lots of things that we would like to do. For SAT solving, proof trimming is important. It's more complicated for pseudo-Boolean proofs. We want to do it. Proofs can get very, very large. We'd like to be able to compress them with having a binary format. As I told you about, ideally, we would like to have a fully formally verified proof checking process. We have this for some settings, but far from all. In general, we still do have performance issues. I mean, we've done proofs of concept, but for several combinatorial optimization algorithms, proof logging and checking is still not fast enough. Lots of work remaining there. It's not clear whether the current proof system can do it or whether you need further tweaks just for efficiency purposes. In terms of other paradigms, it would be nice to do proofs for model counting, do proofs for mixed integer programming. There is a paper explaining how to take the VeriPB proof system and introduce integers and real valued variables. That seems really interesting. There's a lot of work on proof logging for so-called satisfiability modulo theory solving. There, the proof system is much more complicated. So they have sort of a different design philosophy. It would be interesting to see if anything from VeriPB would maybe be useful there. And as my sales pitch on one of the very first slides, once you have proof logs, you can mine them for algorithmic insights, for explainability. I think like once you have algorithms with proof logs, there are all kinds of interesting things that you can do that we could not do before with our algorithms. This is also to say that there's lots of exciting work to be done. You're welcome to join the pseudo-Boolean proof logging revolution if you wish. We who are here today, myself and Kieran, are members of our group. We're happy to collaborate. We're hiring. Come talk to us. So summing up what I've said so far is combinatorial solving and optimization. There has been amazing progress since the turn of the millennium, but solvers are buggy. This is a serious problem. The best solution we have for this today is to make solvers certified so that they produce machine verifiable proofs. It seems that the best format for this that we currently know is to use 0-1 interlinear inequalities and to do reasoning on them using the cutting planes proof system. That seems to be a sweet spot between simplicity and expressivity. So maybe, you should, one of the things that you should think about after this talk and after this tutorial day is if you could maybe use VeriPB proofs for your applications. So thanks. So we're a little bit behind in the schedule. If there are any questions, we maybe have time for 1 or 2 quick questions. Otherwise, we'll take a coffee break. Yes.
Maybe it doesn't make much sense, but to get an idea, if you take a root proof and convert it into your format and check it, what's the overhead of the proof checking time?
It probably depends. If it's a clausal proof, then the conversion is a pure syntactic change, right?
I don't understand. I mean, you do give the IDs of the clauses that you are receiving, right?
I didn't tell you. So firstly, okay, what I didn't tell you about, there are 2 versions of the RUP rule. I only gave you the one that in the VeriPB proof format, you can just say this follows by RUP, or you can say this follows by RUP and do unit propagation on these constraints. And if you give these helpful hints, then in general, the verification will be way faster. So basically, if you just convert a DRAT proof, then you would get RUP statements without these extra hints. If you take an LRAD proof and translate it, then you would get RUP with hints. If you're doing this for a clausal proof, then I think in both settings we're slower. For DRAT, I think we're much slower. This is mostly a software engineering problem. You could have, I mean, if you know that you only have clausal constraints, then we could have optimized algorithms that work really fast for clauses, because propagation on clauses is much simpler than general propagation on pseudo-Boolean constraints. We just haven't like invested effort into that. But I think, I mean, it's getting better. I don't know if we have like RUP with hints. How fast would we be compared to a state-of-the-art DRAT trimmer? Do we know anything about this?
Yeah, not compared to DRAT trim.
Because it's also like one important thing that the SAT proof checkers would do. They would also trim the proofs, and maybe next year at this time we will have a proof trimmer. We're working on it. So I would just say but the latest version, like VeriPB wasn't allowed proof checker in the SAT competition. That has been so since 2023, I think. In previous years, we did have some problems with proofs timing out, and we essentially, I mean, I think you'll see some performance data in the afternoon that most of the time proof checking will not take a factor 10 more than proof solving, and this is sort of the standard that is expected in the SAT competition. For at least for pseudo-Boolean solving and pseudo-Boolean optimization, we're already in that ballpark. For subgraph solving, for constraint programming, I think we're nowhere close, but this is for like a number of reasons. And there, of course, I mean, there you don't have any other proof logging options. I mean, for clausal proof logging, you can't even write the proofs in the first place. But there's definitely room for more engineering. This is still like, you know, we're developing the technology and developing. Anything else? Good, so then let's have a coffee break.